Thanks, Mike. Thanks for the HIP organizers. This is a really wonderful gathering. I'm going to talk today about a method for analyzing clinical data, high throughput clinical data. Actually, it's not just the economists that have toxic acids. In biomedical research, we have our own toxic acids. Among them, till now, we don't have any disease modeling algorithm or a method. In addition to that, built on that, we don't have disease definition and, in a molecular way. So we have no molecular boundaries for the disease. Also, we have no good method to do the subtyping of the disease or early detection, biomarker discovery, profiling, sorting out the clonal from the non-expanded mutations. All of these things are our current toxic acids that we are still working on. So what is really common between all of these? If you solve one of them, you can solve the rest. Because they are all, the problem with them, they are all based on heterogeneous data. And dealing with the heterogeneous data is the problem here. So what do we mean by heterogeneity? We mean that if you take, for instance, in this case, 7 tumors in the same organ, a renal gland, and you do analysis on them, you realize that there are 3 groups of the tumors. So the tumors basically within one organ are heterogeneous. And between individuals, they are also different. And now, by deep sequencing, we know that each tumor also, within it, there is some variation. So the levels of heterogeneity are on 3 levels, within the tumor, between the tumors, and between individuals. So what do we need? What kind of paradigm do we need to solve this issue, to do the modeling and the other subsequent issues? We need a paradigm that can encompass 4 things: the genotype of the disease, the phenotype, evolutionary, theory as the conceptual framework, and the bioinformatic tool that will do that. This new kind of tool that we need should be predictive, seamless, multidimensional, and within the paradigm of systems biology. I think that phylogenetics is the best kind of conceptual framework for that. And within phylogenetics, I selected parsimony as the best paradigm for this kind of analysis. Why? Because it gives us the multidimensional tool that is data-based and not specimen-based. And also, it accounts and integrates the issues that we want, namely the disease heterogeneity, the nature of the data, the high mutation rate that exists, and also the principle of evolution. So what is phylogenetics? Basically, phylogenetics is based on the premise that not all similarity is the same. Similarity is a mixture of ancestral similarity and derived similarity. And by knowing what are the shared derived similarities, we can group things together. We group them in clades. And the clade basically is a group of specimens that share derived variation. And our graphic tool is the cladogram. I'm going to show you an example of that. So what do we need to do the parsimony? Basically, do polarity assessment, know what is derived and what is ancestral, and then run that through a maximum parsimony algorithm. Parsimony is basically selecting the hypothesis, or in this case, the cladogram that is the shortest or requires the smallest number of steps to construct. Here's an example, like 2 specimens sharing the same gene expression or mutation. There are 2 ways of representing it, putting 2 origins of the mutation or 1 origin, so you choose one of those. You choose the simplest one, which is the one on the right. Here's a cladogram that shows that using parsimony you can separate the metastatic prostate cancers from the primary prostate cancer. This is the cladogram. So basically it's a 3 representation of the data. Also here it shows how we can separate the leiomyoma from leiomyosarcoma by using also parsimony phylogenetics. This is modeling the serum metabolomic data. This is from prostate cancer. The patients were treated with radiation, and you can see only 4 of these patients, became normal, and the rest still having the problem of prostate cancer with it. It has a higher concordance. Also, you can pool several data sets, and eventually you can apply this within a clinical setting. Basically, in the future, we envision that you go to the physician, and from a small blood sample, we can run your specimen within a kilogram, and if your specimen comes out in the healthy plates, then you are healthy. If it's in the transitional, then you are developing or accumulating some mutations or changes. If it's in the cancer plates, then there is some cancer. So that's basically the phylogenetic paradigm for systems biology. Thank you.